Hi, welcome to another live star stream of UTA Planetarium. My name is Levent Gurdemir, Planetarium Director and UTA Astrophysicist, and today we are going to talk about invisible protection shield around our planet. So before we start, I would like to say hi to Brexton. Good to see you again, sir. And also, if you have any questions during the live stream, please use the comment chat and direct us the questions. And I have a very special guest today to talk about this topic. So I came across to a very interesting NASA article the other day that talks about the NASA researchers finding a dent in the Earth's the magnetic sphere, magnetosphere. So let's take a look at that article. In the article, you will see our planet with a bunch of lines around it, and they represent the magnetic lines. So, and they were talking about a dent in the system. But first, let's talk about what is magnetosphere or magnetic field of Earth. Our planet has a magnetic field around it. So that's an invisible the force, pretty much like a magnet. The magnets have invisible forces because when you get a charged particle or a metal thing near a magnet, so you can actually feel the force. It is in either in the opposite direction or in the sticking direction. So a force is applied to the objects around the magnet. And our planet itself is actually a magnet in space. That means our planet is also exerting forces on charged particles around space. So that is important because this is actually creating an invisible protection shield from a lot of charged particles raining down on our planet from the sun. So the sun is a good source of that particles, and as we speak, those particles flown into space at high speed, they could be extremely dangerous to us. But thanks to the Earth's magnetic field, the magnetic field traps these electrically charged particles and diverts them away from our planet, and then we don't notice them. So sometimes the magnitude of the wind is strong, and this usually creates a problem for communication satellites because we are away from the satellites are away from the surface. So the particles don't make it to the surface, but it may be intense enough so they can knock down some satellite communications. And in the past, actually, we've seen some on the ground examples of some of the issues created by these charged wind of particles. And to talk about this specific article, I have a very special guest, another UTA physicist with me, Dr. Dan Welling. Hi, Dr. Dan Welling.
Hi, how are you guys doing?
Very good. We are doing fantastic. And I wanted to ask you about this. First of all, could that be a dent really in magnetic field lines?
Yes, I think the word dent is a slightly misleading. I think probably, in my opinion, it's better to refer to it as a weak spot. So when we picture the Earth's magnetic field, we like to think of it as a dipole, or the kind of magnetic field you'd get from a bar magnet, where field lines come out of one end and then go to another, and it's very simple. But in reality, the Earth's magnetic field is very complicated. It's like there's a bar magnet in the center of the Earth that is offset a little bit and then tilted, and then is, instead of like a nice clean bar magnet, it's maybe a little twisted and bent and not very even. So the net result is, instead of nice smooth magnetic field lines, you get some places that are stronger than others. And we actually have a weak spot in our magnetic field centered over South America called the South Atlantic Anomaly.
Could that be pose any danger to the people like us walking on the surface of Earth, or it is just the satellite type danger?
So for us on the ground, we don't have to worry about it. We really, when we're talking about protective layers of the Earth and space, the magnetic field is the first line of defense, but our main armor, so to speak, is the atmosphere. And unfortunately, it takes a lot of energy for a particle to make it all the way from space down to the surface of the Earth. And at that point, the South Atlantic anomaly is we don't have to worry about that at all. However, in space, that weak spot means that particles can get closer to the Earth and closer to the Earth's atmosphere and a little deeper down than they would in other spots. So spacecraft flying over the South Atlantic anomaly need to pay special attention, and space weather forecasters, of which there are now a growing number as space weather becomes very important, need to pay attention to the South Atlantic anomaly because it represents a really complicated area for space weather.
Also, I always heard that the magnetic poles are shifting. They deviate from the north to south direction, and eventually the polarity will be reversed. Do we have any information when that reversal is going to happen? And also, is it going to happen immediately, suddenly, or it's going to be a very slow change in thousands of years?
So those are all really good questions. And the ultimate answer is that scientists don't know yet, but we're working on it. We know from the geologic record in rocks that, as you said, the Earth's magnetic field shifts and eventually will flip direction altogether. But we don't know what that's going to look like or when it's going to happen. It tends to happen on a time period of millions of years. It's been quite some time since we had our last reversal. We don't know if it's going to be a sudden switch. We don't know if it means the Earth's magnetic field is going to collapse and go away and then reform in an opposite direction. We're not sure what that's going to look like, and that's kind of an active area of research. But we do know that the North Magnetic Pole moves, and right now it's moving towards Siberia, towards northern Russia. It tends to do this very sporadically. So instead of a nice, smooth, predictable path, the North Pole suddenly will kind of drift a little bit, and then over the course of a few years, it'll make big jumps, and then it'll slow down again. It's a very confusing thing. It takes a lot of work and a lot of observations to try to understand and predict. And frankly, we're not sure when it's going to happen or what it's going to look like when it does happen.
So, also to my knowledge, the scientists and researchers are constantly tracking the flow of particles from the space, and the one of the source is our star, the sun. And are there any the predictions on what is going to happen with this, especially this the weak spot, whether it is like expanding or narrowing down, or is it something that we don't have any enough data yet to talk about?
Well, I know people are working on it. I don't think we have a good grasp of what the change in the South Atlantic anomaly, how that will affect things overall. But we can expect it to be a factor in the radiation belts. So these are the highest energy particles that are circling the Earth, and those pose a great radiation risk to astronauts and to satellites. So the South Atlantic anomaly represents a spot, a weak magnetic field where those really fast moving particles can get very close to Earth. And when they get close to Earth, they start to run into the atmosphere. And that is a, a loss term, a place that helps empty um, the radiation belts. So it would be easy to say, well, that means that, okay, the radiation belts aren't going to be as full all the time as we expect. But it's actually far more complicated than that. It could mean that for certain types of space weather storms, for just this narrow window over the South Atlantic anomaly, we would expect there to be less radiation. It could mean that if it's a storm that causes the radiation belts to drain very quickly, that may happen faster than we've seen in the past. But with this, with these new changes in the South Atlantic anomaly, where it's actually growing and splitting from a single weak point to two, I think we have a lot more computer modeling work and observational work to see exactly what that looks like.
Brexton asks, is that the only weak area around Earth?
It's by far the biggest one. So I would say it's the only significant one. There may be very, very slight deviations in other places. It's actually kind of an interesting thing to think about physically, right? So the where the magnetic field is the weakest is around the equator, right? So the magnetic fields come out of the north and south pole and they wrap around, and they're very weak by the equator, but they're also, that's the point where the geometry is such that it's perpendicular to the surface of the Earth. So it really, particles don't like to go across magnetic field lines. They like to go around. So particles have a harder time getting in at the equator. Now at the pole, the magnetic field lines are sticking out of the Earth or coming in. And so even though the field is much stronger there, the particles, they don't like to go across, but they do like to go along. So they have a really easy time coming into the North Pole. Oh, and the South Pole too. And that's actually one of the ways in which you get the aurora. So it's, to be very, a little pedantic, it all depends on how you define weak. In terms of the strength of the field being the weakest, the South Atlantic anomaly is the critical part. But in terms of acting less like a shield and more like a funnel that funnels particles into our atmosphere, the North and South Pole have very strong magnetic fields, but those field lines just funnel particles in to the atmosphere and give us the northern and southern lights.
And I can consider myself as an exoplanet scientist, and one of the things we are looking for habitability is maybe not only how far the planet is from the sun, how much temperature is there, and what type of atmosphere it has, and maybe we should also question the magnetic field strength of the planet too, to say that planet can render life possible or not. And is magnetic field is usually we don't hear a lot of news, and it is pretty much, I know, like a maintenance free item around planet. But do we know a lot of things about the magnetic field, or is it something still we are trying to scratch the surface perhaps?
Wow. So in
Is
terms
it worth the
of,
study?
oh, absolutely.
With other words.
Absolutely. There are entire teams in the United States and in other countries who dedicate a lot of resources into understanding how magnetic fields of planets may affect their habitability. Habitability, excuse me. And it's a very big open question. In our solar system, we have our two closest neighbors, Venus and Mars, who give us very contrasting views of magnetic fields. There's Mars that used to have oceans and atmospheres and a strong magnetic field, and now has none of those. It has a very weak atmosphere. It has only what we call crustal remnants of magnetic fields, so only little areas on the surface that have local magnetic fields instead of a big global one. And so that would seem to be a case where, well, maybe that was a planet that was habitable because it had a magnetic field, and the magnetic field went away, and so did the atmosphere. But on the other hand, there's Venus, our other neighbor, and Venus has no magnetic field and a huge atmosphere, a very dense atmosphere. And what makes this a not an apples to apples comparison is that Venus has volcanoes and sources to help replenish its atmosphere. And I want to take this actually one step further and talk about where we are now with the research. So let's think about two cases. A planet with a magnetic field, and the solar wind comes blowing in, and it hits not the planet's atmosphere, but the planet's magnetic field, and then it wraps around and it goes around the planet. And if you think about the interaction of a planet without a magnetic field, the solar wind comes in and it hits the atmosphere and it blows off parts of the atmosphere. Now, you would naturally think that the planet without the magnetic field would lose its atmosphere much, much faster. However, what happens is that the planet with a magnetic field, when the solar wind comes in, it hits the magnetic field and it curls around and it kind of deposits energy into the north and south magnetic poles. And that excites particles and causes them to blow out the poles in what we call the polar wind. And in the 60s and 70s, we had the first satellite measurements of the polar wind. And people didn't think it existed. And all of a sudden, the data came back and they said, there it is. The Earth's atmosphere is blowing out of the North and South Pole at 1 times 10 to the 27th particles per second. That is 27 zeros particles per second leaving the Earth. And if you take observations of Venus, of Saturn, of all these other planets, you tend to see that number pop up a lot, this 10 to the 27th, over and over and over again. So that seems to suggest that, well, perhaps the magnetic field funnels energy into the poles, and so you get the same amount of atmospheric loss with and without a magnetic field. But I need to emphasize this is an open question that we do not yet understand. We need a lot more satellite observations of Venus, of Mars, of exoplanets, and we need a lot more fundamental theoretical research, computer models and everything else to try to better understand, how atmospheric loss works with and without a magnetic field, and if it's a critical piece to having a planet that is a habitable planet or a barren planet.
That's certainly interesting. And also, I remember a very interesting presentation of yours at UTA about some of during Vietnam War, some of the underwater mines exploding because of not the ships passing by, but because of some activities in space. Could you please briefly talk about that?
Yeah, this is a really fun project we're doing here at UTA. Back towards the end of the Vietnam War, the Nixon administration was deploying naval mines, so explosive devices that sit outside of bays and harbors, such that when giant metal shipping freighters come by, they explode, the boats sink, and North Vietnam at the time will not be able to get supplies and munitions from other countries, and it'll strain them. And the way these mines work is one of their triggering devices is essentially a metal detector, right? That feels the magnetic field of a big boat going past, and then your naval mine detects that remotely and explodes and sinks the ship. So the United States deployed tens of thousands of these towards the end of the war to try to get the North Vietnamese to sign a peace treaty, and then the United States could go and clean up all these mines. Well, in August of, was it 72 or 74? There were a lot of interesting space weather events, and I'm forgetting my year. I'll have to look up the actual year. It was in 1972. I'm so sorry. Within minutes, thousands of these mines started exploding with no boats around. And this was a huge disappointment because the United States spent hundreds and thousands of man hours deploying these. It was a huge mission at the time. And all of a sudden, it was gone. Well, it turned out that after a lot of work, the Navy and the armed forces determined that the cause of this was a solar flare, a burst in the solar wind that when it reaches the Earth, our planet's here comes the solar wind, it hits the magnetic field and causes the Earth's magnetic field to shake. And if you're on the ground with a metal detector or an object to measure magnetic field, you see those wiggles in the magnetic field, And if you're a naval mine, you say, hey, there's a boat, I need to explode. And that caused that whole chain reaction of explosions to go off that day. We're actually studying it here at UTA. We're doing computer simulations to try to understand how the solar wind was precisely able to detonate those mines just outside of North Vietnam on that day. It's an interesting experiment for sure.
Thanks for sharing. It's certainly great. And because last week we also talked about some cosmic rays with our audience, and some of the cosmic rays were blamed to corrupt the data in the computers. IBM Computer Corporation has even a statistics for that. Like one data is being corrupted at every 256 megabytes in whatever time. And also they were blamed to have creating some problems for some airliners and even some of the cars. So sometimes trouble comes from space on its own, and that's why researchers are on top of those things and trying to learn, understand nature, and finally they share the findings with you guys. And here you can still ask questions. Probably this is a last live opportunity of the moment, but if you have more questions and if you just read them after the stream, we'll try to answer afterwards. But if you would like to, if you're actually interested in studying physics and space, Dr. Welling is teaching courses at UTA, and his classes are absolutely amazing. All right, so next week we'll be with you with a different topic, and we are also trying to adjust our time to fit this newly started online school schedule. And also we are making preparations for to enrich our offerings. We'll let you know all about those on our social media. And Dr. Welling, thank you very much for being with us today. We certainly enjoyed your presentation and talk, and hope to see everyone next week. Bye-bye.